We're back. Module 5.2, CHE 411 Physical Chemistry 3, Spectroscopic term symbols. You need to pay serious attention to this module. It's very important, and I'm very much sure that there is no exam you will write, you will not see at least one or two questions from this particular module. We'll look at introduction, spin angular momentum, ground state electronic configuration, heteronuclear diatomic molecules, and we'll conclude. Recall that the molecular orbital sigma is that in which the component of the angular momentum about the internuclear axis is lambda equal to 0. And the molecular orbital pi is that in which the angular momentum along the internuclear axis is 1. Lambda equal to 1. That's what we said before. Now, for two electrons having angular momenta lambda 1, lambda 2, the resultant angular momentum along molecular axis is given by lambda equal to lambda 1 plus lambda 2. So for two electrons, we have lambda 1 plus lambda 2. If lambda is equal to 0, then we have this state. This is the sign for the spectroscopic term symbol. We have this state. If lambda is equal to 1, we have this state. If lambda is equal to 2, we have this state. So these are the major three states we have. We get them from lambda 1 plus lambda 2. So if we have a resultant lambda of 0, we have this. This is sigma, lambda 1, this is a pi. And of course, we made this before, the Laplacian operator, inverted delta. So these are the main three states. Spin angular momentum. For any electron, of course, we know that we have a spin angular momentum given by ms equal to plus or minus half. We know this. So if we have two valence electrons with spins S1 and S2, then the resultant spin is given by S1 plus or minus S2. So assuming we have S1 equal to 1 and S2 equal to 1, S1 equal to half and S2 equal to half. So we are going to have half plus half and half minus half. And then the multiplicity is given by 2s plus 1. So whatever s we get here, the resultant s we get here, we'll insert here to get the multiplicity of that particular state. Now the spectroscopic term symbol is therefore given by this E here is representing the sigma, the pi, or the inverted delta sign, which we say there are the three possible states we can get. So any of them, when we calculate the lambda, is what we get here. Now this is our multiplicity, 2s plus 1, which we'll calculate from the spin here. And x, it denotes our u or g. Remember our unjared and jared, depending on the behavior of all electrons to the operation of inversion through the center. This is how we'll get the x. If the number of unjared orbitals occupied by the electron is even, then x is equal to g. If it is odd, then x is equal to u. Now we're using F2 fluorine as an example. So let's take time and follow this step by step. What is the spectroscopic term symbol for F2? First solution F2 has how many electrons? If you remember, who can tell me how many electrons do we have? When we did the electronic configuration, we got 18 electrons, right? From the electronic configuration which we did before, bond order is equal to 1. You can go back, sit down, get a paper, check the number of bonds in bonding orbital, check the number of bonds in antibonding orbital, use the bond order, and see if you get a bond order of 1. Now in F2, we have two valence electrons. Check that electronic configuration again. Since they are in this molecular orbital, lambda 1 is equal to lambda 2 equal to 0. They are in sigma molecular orbital, which we said lambda is equal to 0. Therefore, 0 plus 0 is equal to 0. So our lambda is 0 plus 0 equal to 0. This gives us summation states. Remember, we said if lambda is equal to 0, then this is the state. The spin angular momentum S1 and S2 is given by half plus or minus half, which is equal to 1 or 0. If the spin angular momentum is 1, so we're having two options here, 1 and 0. If the spin is 1, the multiplicity is 2 times 1 plus 1, which is 3. That is triplet state. And we have this. It is said to be paramagnetic due to the unpaired electrons. If the spin angular momentum is 0, that is this one, multiplicity will be 2 times 0 plus 1, which is equal to 1. And we say it's singlet state. And this is what we have, and we say it's diamagnetic. Assuming we obtained S equal to half, assuming our S is equal to half here, then it means our multiplicity will be 2 times half plus 1. 2 times half is 1 plus 1 is 2. And we'll say it's a duplet state. And we'll say it is said to be magnetic. We'll continue with our F2. We just use that to give some examples. Now let us go back to F2. There are 4U. Check our electronic configuration. You see that the unjared orbitals are 4. Therefore, it is what? Even. So we have two options. Remember, our multiplicity is 3 and 1. So, and our state is this summation. So the first one is summation to power 3 and G, because there are 4U. And the second one is summation to power 1 and G. So now that we have two states, we want to check the configuration of these two states. For the first one, our S1 is equal to S2. Our lambda 1 is equal to lambda 2. Our N1 is equal to N2. Therefore, this first one cannot exist. Remember, the two electrons have all the quantum numbers equal, and this is against Pauli's exclusion principle. It does not, therefore, exist. So this cannot exist. Let's check for the second one. S1 is not equal to S2 because S1 is half and S2 is minus half. Lambda is equal to lambda 2 equal to 0, N1 is equal to N2 equal to 0. In other words, we can see that the term symbol for F2 is the second option, that is summation subscript G to power 1, because this other one does not exist from Pauli's exclusion principle. So this is the term symbol for F2. We look at another example using oxygen. Remember, we can also calculate F2 plus or F2 minus, or even F22 plus or F22 minus. So all these things can be asked as a question. The first thing is the electronic configuration, and then you follow this step. Let's look at another one, oxygen. Oxygen has 16 electrons. We did the electronic configuration, if you remember, 2, 4, 6, 8, 10, 12, 14, 15, 16. And here, these are the same energy, so we have 1 here, 1 here. In oxygen, we have 4 valence electrons. You'll be wondering, what are the 4 valence electrons? Look at them. This is a valence electron. This is a valence electron. This is also a valence electron. So if you look at 1, 2 is not filled. These 2 are filled. So our valence electron, this one, and then these 2. Okay, it's even written here. Look at it. Valence electron, valence electron. But this one is already filled, but these ones are not filled. Since for the filled orbital, summation lambda 1 will be 0. And also summation S will be very only partially filled orbitals need to be considered. So we'll leave this because it's already filled. We'll consider these partially filled orbitals. Since the electrons are in the pi orbitals, lambda 1 is equal to lambda 2 is equal to 1. Remember the state is equal to 1. So we have lambda will be equal to lambda 1 plus or minus lambda 2, which will give us 2 or 0. Thus, we have these two states. These are the possible two states we have. The spin angular momentum S1 and S2 is given by S equal to half plus or minus half. So we have S equal to 1 or 0. Hence, we are going to have multiplicity of 1 or 3. Right? I hope we are following. Therefore, the possibilities are these. Remember, we had multiplicity of 3 and 0. I mean 3 and 1. So for this state, this is 3, this is 1, this is 3, this is 1. In other words, I've purposely omitted something. So I will ask you that as a question. What are we supposed to have here? Is it G or U? Go back to the electronic configuration of oxygen and find out how many unjared orbitals we have there. Is it odd or even? And let's know what you're supposed to have here. Now for A, this is 1, this is equal to half, this is equal to half. All these are the same, therefore it does not exist. So this first option will not exist. This is equal to 1, but not the same half and minus half, so this exists. This is not the same, so this exists. This is not the same, this is not the same, so this exists. Now we have 3 that is existing. Now the problem for us now is to find out between these 3, which one is the ground state electronic configuration of oxygen. Ground state electronic configuration. So the question now is what I've asked, which of them is the ground state for oxygen? Recall, we had this, that is 2 electrons in 2 different atomic orbitals. The lowest state is that in which the 2 electrons have equal spin or parallel spin. Also, according to Hund's rule, the lowest state is the ground state, or the ground state is that of maximum multiplicity. Remember how we calculated our multiplicity. If we apply this rule, the ground state of oxygen will be represented by this. Remember that that's the one that has a maximum multiplicity of 3. The other 2 states, that is this and this, are excited states of oxygen. We have looked at homonuclear diatomic molecules. Here we just want to mention heteronuclear. When we say heteronuclear, homonuclear, hydrogen, hydrogen, the same nucleus, chlorine, chlorine, the same nucleus, fluorine, fluorine, the same nucleus, oxygen, oxygen, the same nucleus. But when we say heteronuclear, if you have hydrogen and chlorine, it is no longer the same nucleus. If you have maybe oxygen and fluorine, it is no longer the same nucleus. Now, in this case, when we have something like hydrogen and chlorine, the electronegativity comes to play. The electrons are no longer shared equally between the nucleus 1 and nucleus 2. But the one that has a higher electronegativity will attract the electrons together. Therefore, for heteronuclear diatomic molecule, the condition of C1 equal to plus or minus C2 no longer holds. In fact, we're introducing polarity to the system. The electron tends to concentrate on one of the atoms. Heterogeneous molecular orbitals are formed by a combination of these to obtain phi minus and phi plus. Energies of molecular orbitals are formed by a variation method. U and G are no longer applicable to heterogeneous or heterogeneous molecules since symmetry no longer exists. There is no longer symmetry like HH. When you have HCl, no symmetry again. Therefore, C1 is no longer equal to plus or minus C2. Thank you. We have come to the conclusion of this module. We looked at introduction to spectroscopic time symbols, spin, angular momentum, ground state electronic configuration, heteronuclear atoms, and we calculated the spectroscopic time symbols of some molecules using oxygen and fluorine, and of course looked at what is called ground state or excited state of the molecules. I hope you enjoyed this lecture. I hope to see you in the next module. Thank you very much and God bless you.